Alright everyone, in this video I'm going to show you how to model the likelihood of an event with probability distributions. Now, why do we need probability distributions as data scientists? Why do we need to know about these? Well, probability distribution describes how likely an event is to occur over the possible range of variable values. And this description allows a data scientist to know what might constitute an outlier value that could throw off analysis and yield an erroneous so-called insight, and also whether the data needs to be manipulated or transformed, for example, into a normal distribution to better work with certain machine learning models. Scikit-learn, for example, quite often won't work very well if your data distribution isn't normalized. So now let's take a look at some sample probability distributions and get a feel for how these can help you. Okay, so here I have a Jupyter notebook. We're going to look over some probability distributions, starting with the uniform distribution. An example of this would be when you're rolling a fair die. So if you have a six-sided die where you have numbers 1 through 6, each of these numbers is equally likely. And I have a little bit of code here that's going to generate 1,000 rolls basically and generate a number between 0 through 5 for these rolls, add 1 to it, and then plot a histogram with 6 bins. And so as you can see here on the x-axis you have values of 1 through 6, and then if you divide 1,000 by 6, that's going to be 166.67, and as you can see, the number of instances of this die coming up 4 here, for example, is 150. Here you got one coming up 175, and the others are just kind of falling somewhere in between. So that's pretty uniform across what we'd expect if we're just rolling a die at random. Okay, so that's an example of the uniform distribution. It's relatively uniform across all the possible values. Now let's look at the normal or Gaussian distribution. And this can be used for modeling things like the heights of adults, newborn baby weights, ball bearing diameters, and so on. Let's generate some random numbers with a normal distribution here and see what pops up. So we're going to have a desired mean of 0, a standard deviation of 4 in this example. We're going to generate 10,000 values and plot a histogram across 500 buckets to see how that looks. And as you can see, it's generating here what has traditionally been described as the bell curve, right? Because it looks like a bell. And that's the normal distribution. Now, just as a sanity check, we can check the variance value over these values to see whether it's equal to the square of the standard deviation, which is 4, right? And we run that and we get 16. So that's coming out to what we'd expect. Okay, moving on, we have the exponential probability density function. This here is starting out high, and as we sweep across the x-axis, it's dropping off at an exponential rate, which is what we'd expect in an exponential curve. It's just another probability distribution, basically. We call it a probability density function. Now, what happens if we have a coin flip, and we do that over a whole bunch of times? The distribution for that is called the binomial probability mass function. Each flip is independent, has the same probability of success. So if we're to look at this plot here, we can see this distribution, which is similar to the normal distribution, but it comes out looking like that. And the Poisson probability mass function, we could use this to find out, for example, what are the odds of getting exactly 325 customers on a given day, given that on average my store is getting 300 customers per day. So we have a mean of 300 here. You can see the x-axis value here is 300, right in the middle there. That's the top of the curve here. And we're just plotting the Poisson distribution, all right? And so if we look at where 325 falls on this curve here, the odds are looking to be somewhere around 7%. Okay, excuse me, 0.7%. Okay, now moving down here, we are done. Okay, so that was just a sort of a sampling of some probability distributions that can help you to understand your data, get better insights, more accurate insights from your data. And again, if you're winding up with something that's not a normal distribution, you can transform that with mathematical functions to more closely approximate a normal distribution if that's what you need. Okay, so thank you for watching, and that's all for now. See you in the next video.